right. Hello, everyone. Today I will be giving a non-research talk, but going through how we can manipulate tabular and a little bit on images, how we can manipulate really like astronomical catalogs in Julia, and discuss some kind of design choices that go into it. Really, why all sky catalogs, why I'm talking about them here, because no matter if you do galactic, extragalactic astronomy, no matter what wavelength range you use, you often need to work with catalogs, like survey images and stuff like this. Maybe I'm personally, maybe I'm working with all sky catalogs more than an average astronomer, but still I think it's common in many fields. I would say that in the past few years, we've seen Julia ecosystem, both in general and for working with astronomy catalogs specifically, it's been maturing. It exceeds Python counterparts in some cases, but still some pieces are more difficult than they should be or they are missing. So in this talk, I will give just kind of a few examples, a walkthrough of how to kind of get access to some like all sky tabular catalogs, how to plot them nicely and conveniently, how to cross-match them, and how to cross-match them with images as well. And then I'll discuss a few words on like how to design your functions and data structures for extensibility. First of all, obtaining data. I really like that in Julia you don't really need like custom fancy data structures for a lot of things, including astronomy catalogs. They can be just kind of lightweight Julian tables, basically in the simplest case, vectors of named tuples. So unlike what AstroPy does, AstroPy has a special AstroPy table type that is not the same as pandas, not the same as like NumPy. So in Julia we just don't need that. We can very easily use the built-in structures. So here I show an example of, I hope it's visible. Yeah. So an example of how to access Virtual Observatory, like catalog available with Virtual Observatory protocols. You can use arbitrary SQL expressions. It's the same execute from DB interface that is in Julia. And then the only astro-specific part here is really, astro-specific type here is a SkyCoords objects. Otherwise, it's kind of what you generally do in data manipulation. Of course, sometimes you have catalogs as, oh yeah, and I forgot to tell that in Virtual Observatory you have the benefit that all units, everything is automatically parsed correctly, so you don't need to care whether like your coordinates are radians, degrees, seconds, or whatever, they always are correct. You need to be a little bit more careful when loading catalogs that are just plain CSV files. That is also very common, and I think like it's the best practice, but and I really encourage everyone to follow something like this. Is immediately when you read a catalog or any other data set, really try to convert the values you need to proper units or types. Like here, for example, I load an catalog of IceCube events, and I immediately convert it to like just raw columns with array and deck to SkyCoords. I create the kind of coordinate uncertainty. So for your purposes, it may be like just add units or use your other kind of like domain specific type. But this is nice to do at the first place immediately when reading, and then don't care much about potential issues downstream. So plotting is, I think, is a very strong side in Julia here because most notably SkyCoords and also Uncertain.jl have direct integrations with Makie. So you can just plot your SkyCoords objects. You can plot them with GeoMakie as I'm showing here. You can plot them like with regular axis. And it works like for lines, as I shown with a galactic plane. It should be kind of straightforward to see what's going on here. And for source catalogs, and this is kind of a great example of also if you have a type that makes sense to plot at all, just add convert arguments for Makie. It can be easily done in your package extensions. So GeoMakie is just the current way in Makie to plot in spherical coordinates. It has some sharp edges, but for lines and scatter plots, it works pretty consistently in my experience. And of course, given that it's Makie, you can just explore the plot and zoom it in. It's just very seamless. Nothing extra is needed. This is built into Makie. Okay, as I said, plot recipes for everything, not just coordinates themselves, but coordinate uncertainties. So I just call poly and There is a recipe that's saying, okay, how to convert uncertainties in the sky to polygons for plotting. That also works seamlessly. Then cross-match. FlexiJoins is a package I developed, and I will be giving a dedicated talk tomorrow. It is like for joining all kinds of data sets, from simple key-based joins to cross-matching like sky catalogs. Oh. So arguably, it's the most featureful among fast joining libraries in any language. At least I haven't seen any alternatives. It's designed for both flexibility and performance. So, for example, I use it also to perform like Monte Carlo simulations. Let's say like perform a Monte Carlo simulation 1,000,000 of times and calculate some p-values. Whenever I kind of describe it to other people using Python for that, I always hear like, oh, really? It runs in like just 10 seconds for like 100,000 or 1,000,000 iterations. We need to run it overnight. They use some AstroPy tools, and probably they also have some other inefficiencies. But anyway, this is like really designed to be flexible, but also performant. And of course, after doing the cross-match, you can plot the cross-matched object. You can plot like text labels and everything. And what I really like is that you have this in Makie. You have the same code, the same recipes, everything if you use GL Makie, you get this interactive exploration thing and faster plotting in general. Then if you like tweak some visuals and want to save this plot as your kind of publication quality plot, you just switch to Cairo Makie, and it's almost seamless. You don't really need to do anything. That's for tabular catalogs, for sky images, and especially for all sky images. There is also the package I developed, SkyImages.jl. It supports all kinds of things with the same interface, from all small fields to full sky, both fits world coordinate system and hill peaks with the same interface. You can, so this is a firm image. You can, of course, just plot it. Image plotting with GeoMakie breaks from once in a while, so it's fiddly. How it works? It is really kind of image is a keyed array from AxisKeys.jl for maximum interoperability. It's not a custom type. Custom types only appear inside for AxisKeys. Okay, of course you can look up the image at any coordinates. And almost my last slide regarding designing your data structures and functions for extensibility. I would really argue for using generic containers as long as possible. For example, not custom my table, but like vector of name tuples or struct array. Not custom my image, but keyed array, and so on. And of course, sometimes you need to introduce custom types. I argue that they are better introduced at the innermost level possible. For example, not like SkyCoords with circular uncertainty, but just circular uncertainty and use uncertainty packages that support that are flexible enough. Not world coordinate system-based image type, but VCS-based lookup type for that image. There are exceptions, but I think these guidelines help with interop that is crucial for kind of success of Julia and stuff like this. So to sum up, really, I think that we have a rich Julia ecosystem for working with astronomy catalogs and data sets, from tabular catalogs to images, from data access to analysis. Both astronomy specific and general purpose packages can be used for that. There are some pieces missing here and there, but I find that it's easier to fill them on my own in Julia than if I was missing something in Python and wanted to implement it and make it fast. That's why I really encourage package authors to keep extensibility in mind as potential educators, people working with students, to promote tinkering and understanding algorithms, how they work, not just the user-facing interface. That's basically it. I didn't say anything about VLBI today, but I have a poster on VLBI data.jl and the companion packages showcasing the functionality and some interactive tools that are kind of like end-user facing. That's it from my side, and I'm happy to answer any questions now or in the discussion sessions that will be starting soon, I guess.
Thanks. Questions for Sasha?
Okay, great talk. Yeah, one of my questions is actually related to your table join. You know, a lot of big surveys especially LSST, just to name one that's open at the moment, are spending lots of money to rewrite new softwares for new table types and database types, just to do cross-matching multiple epochs of observations to build up detection catalogs. I mean, is this so performant that we should just do this instead? I mean, does this replace a huge database for a survey like that? What is the limitation? What's the breakpoint here?
So FlexiJoins itself, it works on in-memory datasets. For out-of-memory, I mean, support for SQL is pending with SQL collections.jl. With DuckDB, I think you can do a lot. Out of core is, I mean, I don't have like an experience in implementing out of core algorithm myself, but interfacing to DuckDB is potential. Also, I didn't show it here, but you can do cross-match with some tables that is available remotely on the Virtual Observatory server. I use it with Gaia sometimes, for example. I don't want to download the billion of Gaia objects.
On a related note, one thing that some of us in the doing population analyses kind of pine for is being able to do probabilistic catalogs, where maybe you have objects which are clearly detected, but then something in the middle where there's lots of low signal noise detections. And is that something that enters into this at all, or in the future?
So I would say that the FlexiJoins itself, it is for joining on some deterministic predicates. And as I understand, whenever you are talking about probabilistic joining algorithm, the first step is to have a deterministic join with some kind of relaxed criteria, and then refine it with probabilistic arguments. So this is for the first step, because there are so many choices you can make on the second.
Makes sense.